Hello everyone, welcome to my videos on differential equations. This is the second video for chapter 3. We consider second-order differential equations with constant coefficient, and we will explore an algorithm to solve this equation using the characteristic equation. Okay, so to get started, this is the equation we will be dealing with, where a2, a1, a0 are constants, and the right-hand side is 0. So how do we find solutions of this equation? So based on the example in the previous video, we have a feeling that it might be a good choice to guess a solution of the form of an exponential function with a certain rate. So we will try to seek solutions in this form, that is, y of t is e to the power rt, and this r is the rate. And we will try to find values of r such that this will become a solution for this equation. Okay, so now let's plug the y in, and we see that we need to compute y prime and y double prime. So let's do that first. Y prime will be differentiate this in t, and then we'll have r in front of the exponential function. We see that it's just r times y. And y double prime will be differentiate this one more time, and it will actually be r squared e to the rt, and e to the rt is just y, so this is r squared times y. So we see that in this function, e to the rt, seeking solution in this form, and then each time we have a derivative, it results in multiplying the solution with a constant r, and then second derivative will be a constant r squared. So we kind of we transform the derivatives into an algebraic product. Okay, so now let's put these in. So a2 y double prime becomes a2 r squared y, a1 y prime becomes a1 ry because that's y, and then a naught y equals 0. So we have this equation now for our guess. This equation must be satisfied for all the solution y and then your choice of r. Now, if we look at this equation, since it's homogeneous, we know that y equals 0 is always a solution. So that is called the trivial solution. And we are only seeking non-trivial solutions where y is not 0. Okay, so now we can assume y is not 0, and we realize that it's a common factor, so we can just drop it, and we get an equation that's a2 r squared plus a1 r plus a naught is 0. And this is an equation to be satisfied by this rate r here. And we know a naught, a1, a2 are constants. That's already given in the equation. So this has a name. We call this the characteristic equation. So it means that if e to the rt shall be a solution for this problem, then the rate r must satisfy this equation. Okay, so let me also point out a quick way of writing out the characteristic equation without having to go through this derivation step, based on the observation that y double prime will introduce a r squared in front of y, and y prime will introduce an r in front of y. So you can basically take these three coefficients that you already have in the equation, and in the place of y prime you put r squared, and y double prime you put r squared, y prime you put r, and where you have y you put 1, and you form the equation, which will be the characteristic equation. Now, looking at the characteristic equation, we see that it's a quadratic polynomial in R. And we know that it doesn't necessarily always have a real root. But from the discussion, we can conclude this so far. That is, if R is a real root of the characteristic equation that we managed to find, then we know y equal to e to the RT is a solution. We can also say the following. If in the case the roots of these equations are two real and distinct roots, R1, R2, not equal to each other, then e to the R1t is a solution, and e to the R2t is also a solution. Then we can form a linear combination, multiply one by an arbitrary constant, and the second one by another arbitrary constant, and add them up. Then this function here is called a general solution. Here the arbitrary constants C1 and C2 are to be determined by boundary condition or initial condition, whichever is the case for your equation. Okay, let's take a simple example. Now we want to solve this equation. Y double prime minus 5y prime plus 6y equals 0. We need to complete 3 tasks. A, find the general solution. B, now if this equation shall satisfy some initial conditions given as y0 is -1, y prime 0 is 5, I want you to find that particular solution. And part C, have a discussion on the asymptotic behavior of the solution as time goes to plus infinity. Okay, let's do part A. So we know we need to set up the characteristic equation. So y double prime gives me r square, y prime gives me r, where I have y, I put 1. So I have that equal, sorry, there's a 0. Okay, so that's the characteristic equation, and we can factorize the left-hand side, and it becomes r minus 2 times r minus 3 equals 0. And therefore we have two real roots. R1 is 2, R2 is 3. They're real and distinct. Then from the discussion on the previous slides, we know that the general solution can be formed as C1 times e to the R1t, which is 2t, and plus C2 times e to the R2t, which is 3t. So this is a general solution for any arbitrary choices of C1 and C2. Okay, so now we have the initial condition. Let's fit in. So first condition is y0 is -1. So we put t equals 0, and the left-hand side we just get C1 plus C2, which shall be -1. And the second condition is y prime 0 equals 5. So let's compute y prime. And if you differentiate this term, you get an extra 2 in the front. And the second term, differentiate e to the 3t, you get a factor of 3 in the front. So that's the y prime. And now set t to be 0 here. Y prime at 0 will be, this is 1 and this is 1. So it's 2c1 plus 3c2 equals 5. So we see we have two unknowns, C1 and C2, and we have two equations, two linear equations, this one and this one, and we know how to solve it. Okay, so there are various ways of solving this. Let's just quickly introduce one briefly. So using the first equation, I have C2 is -1 minus C, and then we can plug that into the second equation. So C2 is replaced now by that. So we get this equation with only C1 that's unknown, and then you can easily solve it and find C1, which is -8. And then I can plug C1 in here to find C2, will be -1 plus 8, so it's 7. Okay, so then the solution that satisfies the initial conditions is this one. It has a -8 in front of e to the 2t and have a 7 in front of e to the 3t. Okay, now let's try to answer the question part C, that is the asymptotic behavior as time goes to plus infinity. So if we look at the solution written in this form, it's a sum of two terms. This is in exponential growth, and so is that. So when t goes to infinity, the first term goes to negative infinity, and also the second term will go to positive infinity. So what will the sum go to? So it is unclear to look at them in this form. So what we do is we think e to the 3t is e to the 2t times e to the t, then we can take out a factor e to the 2t. Then we get -8 plus 7 times et. So we write this into a product of two terms. Now it's clear, when t goes to infinity, this term goes to infinity, and then this term goes to infinity while this is a constant, which will not matter. So we have infinity times infinity, and therefore the product will go to infinity. So we can conclude y will go to plus infinity as t goes to plus infinity. So from this discussion, we also observe that if you have terms of exponential function that are adding up together to determine the asymptotic behavior, you need to focus on the term with the highest rate of growth. Here 3 is bigger than 2. Therefore, this term will dominate after a while, as we can see from here. And then the asymptotic behavior will be determined by how this term behaves. So here we'll go to plus infinity. So we are given this equation here, and we are given also an initial condition. So the tricky thing here is initial condition is not given at t equals 1. Okay, y at 1 is given and y prime at 1 is given. Okay, so in order to find the solution, we'll still have to go through the proper steps. That is, set up the characteristic equation, find the roots, form the general solution, and then use the initial conditions to find the constants C1 and C2. Okay, so let's go through that. So hopefully it's rather easy for us to set up the characteristic equation. So I have 2 times y double prime gives me r square, y prime gives me r, and then minus y is just minus 1. So we have that. And we can factorize it. It becomes 2r minus 1 times r plus 1. If you're not a big fan of factorization, you can use the formula to solve quadratic polynomials. It will give the same answer. Okay, then solving this, set this to be 0 and this to be 0, we have 2 roots. One is half and the other is -1. Okay, put that in and we can have the general solution. So yt is c1 e to the half t plus c2 e to the -t. Just putting in the r1 and r2 here in front of t. And now let's put in the initial condition to find the constants c1 and c2. So y1 equals 0. So let's put t equals 1. So I have c1 e to the half plus c2 e to the -1 equals 0. That's the first equation. And then the second condition is y prime at 1 is 3. So let's first do the y prime. Then this term is multiplied by half, and this term is multiplied by -1. And now we plug in t equals 1, then it gives me this, and this shall be 3. Okay. Now don't freak out. Here it looks a bit complicated, but this is a number. E to the anything is just a number. And then we know that C1 and C2 here, and they are the unknowns we want to solve. And this is just a linear equation, and that's a linear equation as well. Okay, and call the first equation A, the second equation B. I see that if I add the two equations up, C2 is gone. Then I just get C1, which I can solve, and I found that C1 equals to this number, 2 times e to the negative half. And then we can plug this C1 back into any equation, A or B. Let's do for A, and we can solve for C2. So C2 will be negative e times C1 e to the half. Put in the value of C1, which we just found, I get that. And I can simplify a little bit. Okay, the C1 is 2 times e to the negative half. So I lost a negative sign, so I put it in here. And then these two terms product to be 1, I get negative 2e. Okay? Okay, and then we can plug those C1 and C2 in, and then plug in C1, plug in C2, we get that. And then we see that the e terms, we can collect them together by adding up the powers. If you do that, for both of them, I will get 2 times e to the half, t minus 1, and then the second term is negative 2, e to the power negative t minus 1. Okay, if we wish to discuss asymptotic behavior, here it's easier because this is an exponential growth, and that's exponential decay. As t goes to infinity, this term goes to 0, and this term blows up to infinity. And you add them up, y goes to infinity. And now you may have noticed the computation to find C1, C2 is a bit heavy in this example, heavier than the previous one. And I bet you're thinking that this is caused by the fact that the initial data is given at t equals 1, not t equals 0. And therefore you have all these exponential function terms in the calculation you have to take with you. If you don't find that bothers you, that's fine, you can stick to that. If you want a cleaner way of dealing with this, then let's make a further observation. That is, for the final solution, we managed to write this here as t minus 1 and t minus 1. So t doesn't occur, only t minus 1 occur. And at the initial time, when t is 1, we will actually have 0 here in the exponent. Okay, so this suggests a better way to form the general solution that will lead to simpler computation to find the constants. Okay, let's look into the details. So now I write my general solution as take a function t of t minus 1. So wherever I have t, I just put t minus 1. And then I have constant C1, C2 with a bar to mean that they're a different constant from the other formulation. And we see that we can do that for the following reason. If we look at this term, it's essentially e to the t times half times a term e to the negative half. So you can think C1 bar times e to the negative half is an arbitrary constant since C1 bar is arbitrary. Okay, and for the second term is the same. This is e to the negative t times an e. So I'll have C2 bar times e as an arbitrary constant if I only take this term, which is again an arbitrary constant. Okay, so this trick can be played not only for initial data given at 1. If you have t naught as your initial data, you can replace t with t minus t naught, which would simplify the computation later on. Okay, let's see if this really simplifies anything. So this is our general solution, and we know that y prime is needed. So let's compute that. That is, multiply the first term by r1, which is half, and second term by r2, which is -1. Now we put in the initial condition, y at 1. And then we see this is 0 and this is 0, so I just get c1 bar plus c2 bar is 0. And y prime at 1, so you see this is also 0 and 0, so we get a half c1 bar minus a c2 bar, and that's 3. So now you see these two linear equations for the constants are much simpler. You don't have these annoying e to the weird number terms occurring here. Okay, and it shall be rather easy to solve. You can add the two equations, then find c1 bar, and then use that to find c2 bar. So you find one is 2, one is -2. So we can plug it in, and we have the solution with the c1 bar and c2 bar here. And of course, if you compare this to the final form we got by using the first method, by rewriting it as this, they are the same, of course, because the solution is unique, which is the theorem we will learn very soon. Okay, so let's do a summary of what we have learned so far. The summary, kind of a recipe. Okay, what we have learned so far. Okay, so first step is to write the characteristic equation. And the trick is replacing y double prime with r squared, y prime with r, and y with 1. And then we solve this quadratic polynomial. We find the roots. Once we have the roots, in this case, they are two distinct real numbers. So far, we have considered only that case. We write the general solutions with the arbitrary constants c1 and c2. And then we will use the initial conditions, or sometimes it might be boundary conditions, and to get these constants c1 and c2. So we have the solution for the initial value problem or boundary value problem. Okay, so we have only considered the case where the two roots r1, r2 are real and distinct. So I'm sure you are thinking, what if that's not the case? Because one could have repeated roots r1 equals r2, or that there are no real solutions, so we have to get involved with complex roots. What happens there? Okay, and of course, this is only the first simple case we discuss here. There will be more cases and more examples to come in the future videos. Okay, so I hope you enjoyed this one, and I look forward to see you next time.